I would like to thank Milos for this invitation and the opportunity to present the new work on our lab on the indentation. We try to investigate the effect of hydrogen on mechanical behavior on the subsurface, on specific orientation. And we focus my talk on nickel alloy, pure nickel, with different single crystal with different orientation. It's a part of work of a different student, and I'd like to thank also my colleague for that. Okay. Right. It's not okay. Excuse me. Oh, sorry. We start by we start by answer some results on the bulk behavior. And in the past, for single orientation here, or for multi-slip orientation, single crystal, we have shown that when you added hydrogen, we have a softening but hardening, and hardening in this place, and here a softening, and in the early stage of the deformation, hardening. And we have the same results for cyclic strength and curve, and is the results of École des Mines, the David Delafosse group, and also our group on multiple slips show that we have softening and hardening, which depend on the plastic strain amplitude imposed. And if you focus on the bulk crystal, in recent work, we show that when we added a different content of hydrogen, we have a softening of hardening, which is difficult to question that. In terms of model, it's now well known that hardening is linked to the increase of the mobility, the difficulty of the mobility of dislocation, because we have a drag stress imposed by the coated atmosphere of hydrogen. The softening is linked to the shelding, it's a decrease of apparent elastic properties, and hardening is also, for large plastic strain, linked to the reduction of interwall spacing, which describes the cell structure. Well, in subsurface, we have a nice work on Barnouf team. Firstly, we perform nano indentation when during the charging condition, and show that in a load depth picture that we have a softening during the popping events. And another situation is interesting with the German team, which shows that we charge in opposite sides that we impose an indentation, and also observe softening and hardening in this situation. More recently, we performed the same work on a 1-1-1 orientation during the, we pre-charge and then perform indentation during the desorption. And we show that we have a competition with hardening and softening also. Then the question of today is what kind of effect on the crystallographic orientation, firstly, the charging conditions, the depth of the indentation, the hydrogen content at the early stage of the generation of the plasticity. Here is the early stage of deformation, here is generally plasticity. Well, first, we tried to question the impact of crystallographic orientation on the local diffusivity and solubility. We answer some results of our lab on that. Then the second step, we tried to follow the evolution of diffusive hydrogen, deep trapping hydrogen, vacancy and vacancy cluster during the absorption of hydrogen. And then we can try to discuss the impact of both processes of mechanical properties. And we use the different crystallographic crystal, it's 100, 1110, and 111. And also we have another orientation. Okay, the first results that we need to answer is obtained by Jackie Lee a long time ago, which shows that the diffusivity of hydrogen nickel single crystal is anisotropic when you add hydrogen. And here we have the evolution of the flux, time for specific orientation, and shows that this flux depends on the condition of charging. And we can represent the apparent diffusion coefficient as a function of the concentration of hydrogen obtained on this sample after this technique by TPS. And we show that apparent diffusion coefficient increases with concentration of hydrogen. We depend on the concentration of hydrogen we added on the material. The second result is the fact that the flux depends on the orientation when we're charging the surface, and we have anisotropic results. This result is managed with a specific map, it's under small figure, and we represent tensor of the diffusivity in this map. We have shown that we have a high diffusivity near this orientation and the low diffusivity in this orientation. this inverse Paul figure is quite similar that Y. This parameter describes the anisotropy of elasticity in this material, and we show that we have a nice correlation. And to manage this effect, we use a thermodynamic process and implement the effect of elastic distortion induced by a defect on the potential chemical potential. And we show that, in fact, to describe that, we need a cluster of vacancy of 5 nanometers. By perform TM, we check that and we observe that. In fact, then the anisotropy of diffusivity of hydrogen in nickel is induced by the production of vacancy during the ingress of hydrogen. The second interesting talk is the fact that we can check also the surface behavior. We perform pulse electrochemical technique, we charge on the surface and stop this charging condition, and then follow the flux during the desorption. And this kind of curve, and with this curve, we can modelize this with Fick law, modify with Fick law, like that, and extract the apparent diffusivity. And then we can represent the apparent diffusivity, the diffusion of the apparent diffusivity, as a function of the distance when we ingress the hydrogen on the surface. And we show that we have a gradient of this apparent diffusivity, which depends also to the orientation study. And the amplification between the subsurface and the bulk is a factor 6 in this orientation and is modified by this orientation study. And the high value is obtained for 111 hole. It's important to answer that, and we show the consequence of damage after mechanical behavior, also nano damage. For resume our observation of vacancy, it's important to shows the nice relation with the concentration of vacancy and the concentration of hydrogen is quite linear in the domain explore. And this curve is a pure single crystal. And when we impose dislocation to restrain this single crystal, we have a shift of this curve. And when we measure this concentration of vacancy with a polycrystal material, we have also a shift, which means that the pre-strengthening of the initial density of defect impact after this relation. This production of hydrogen in bulk has been checked with TM is 3 months ago here, but it has been also observed in subsurface in a distance with 1 micrometer when you compare gaseous charging and cathodic charging. We show that for the same thermodynamic condition, when we try to shift the surtension to the fugacity, we have not the same density of vacancy. It's interesting results for the future. We follow also the evolution of the concentration of hydrogen with different type, and also the concentration of vacancy using different techniques is resumed like that. And here we show during the desorption for the 1 orientation nuclear is the total density concentration of hydrogen. It's diffusive of hydrogen, and we need 3 months to have a complete desorption of hydrogen after precharging of 7 weight ppm of this material. And we follow also the concentration of vacancy. We show in the early stage that we have a less increase of the concentration of vacancy during the desorption step, and also an evolution increase of the concentration of deep trapping in this same domain. And the second domain, we have a decrease of both components. And it's interesting to compare both to question the two regimes. In the first regime, the fact that the concentration of vacancy is higher than the concentration of deep trapping, which means that we have a more production of vacancies at the deep trapping process. And the second domain is the fact that CTIR is higher than the concentration of vacancy, which means that we have a more trapping process than the superabundant vacancy process. Now try to check the effect of these results on the indentation, which perform indentation for different surface, for specific preparation of the surface. And then we perform with a pre-charging situation, nano indentation just after. We perform the first indentation 20 minutes after the charging condition. Okay, we discussed 3 domains. The first domain is elastic domain, which can be modelized by Hertz model. Second domain is a popping, we have the emission of dislocation. And the third domain is a large deformation and is hardening the range domain. And we show firstly for the elasticity, for each orientation, we have a loss of the elasticity place, but the impact of hydrogen is different as a function of the orientation. The minus is maximum in 1110 is this orientation. We have a large diffusivity. Oh, sorry, okay, we accelerate. Okay, the result of effective modulus as a function of orientation factor, like that. HKL is the orientation of the plane. And we compare here the effect of the orientation without hydrogen, and here is the result with hydrogen. The main effect of is softening, and it depends on the orientation. To discuss that, we use diffusivity, and we use also modularized atomistic calculation. Two kinds of approach, we do not describe that. The first reason is the fact that the main softening is obtained for the large diffusivity, the 1110 compared to 100, and is directly linked to the production of defect, which shows that the vacancy concentration is higher in 1110 than 100 when we introduce hydrogen. Another interesting feature is that in this orientation will produce also dislocation, which means that probably we have produced metasable hydride, which disappear after when we perform TM observation. To question that, we use atomistic calculation and show that the effect of softening in the elastic modulus is not linked to the concentration of hydrogen, because hydrogen concentration increases elastic modulus, but it's induced by the production of vacancy. When you did a vacancy on the box, we show that we have a softening. And the effect is largely in subsurface as in bulk, because we have a large elastic pressure in the surface during indentation. Now, during the desorption, we show that a specific decrease of the effective modulus that you have present, but we have a progressive recovery, but not completely recovery, because not completely recovery the concentration of vacancy during the desorption of hydrogen. Now, for the popping, is characterized by a load and the length. And we show that we have here a reduction of popping and here an increase. And we have a competition with hardening and softening, independent of the orientation. And we show that the popping can be represented by a linear curve to relate the load and the length, and is classical for the burst process. And we show that for the orientation 110, we have a hardening effect of hydrogen. And for the other orientation, we have a competition of hardening of softening, which depends on the length. And if you try to explain that, we try to correlate the softening by the decrease of the elastic modulus as a concentration of vacancy, and the hardening as the strength of the strengthening of the solid strengthening is well modeled by the model. We don't describe that, but it is during the desorption. The last result is the fact we have hardening in each domain, each orientation for large deformation, which is linked with a simple model to the increase of density of dislocation. And this dislocation density increase when we added hydrogen in all the orientation. And if you check that, we perform FIB sample and observe the dislocation density near the tip and show that we have a large increase of density of dislocation when we added hydrogen. It's a result of this curve. This is death, and the density of dislocation as a function of the death of the indent. With nickel and with nickel with hydrogen. And we can conclude with the effect also to a vacancy. This increase with added hydrogen on the density of dislocation can be linked to the vacancy or hydrogen or both. And to check that, we use the EAM atomistic calculation and shows the evolution of the density of dislocation as a function of the death. Red curve is with vacancy, the blue curve is with hydrogen, and the dark curve is without anything. And we show that hydrogen decreases density of dislocation, and the vacancy increases density of dislocation, which means that the vacancy produced is responsible to the increase of the density of dislocation. And we can correlate also the effect of density of dislocation and the addition of hydrogen, which means that if you have here no hydrogen, the concentration of vacancy for that one as a function of density of dislocation. When we added hydrogen, we have a large increase of the production of vacancy during the deformation. And this result is well correlated with the experimental data. Thank you for this presentation.
Thank you very much. So if you have one short question.
We have the same message. We have a bit few next year in La Rochelle for a joint conference.